In this video here, I gave an overview of a very simple Aldol reaction, just to get the basic principles in line. That video was about acid-catalyzed Aldol reactions and aldol condensations of acetaldehyde. Let's look then at aldol chemistry under basic and acidic conditions for various electron withdrawing groups. Always, when you confront a problem on aldol chemistry, ask yourself, what is the pH? If the pH is greater than 7, it's base-mediated. If it's less than 7, it's acid-mediated. Base-mediated is enolate chemistry. Acid-mediated is enol chemistry. Separate those in your hard drive because they proceed via different mechanisms. And let's not consider the electron withdrawing group, EWG, at this time. We'll draw the enolate formation as simply as it possibly can be drawn. A base approaches a molecule with an electron withdrawing group, EWG, and an alpha CH, which is acidic because it can form an enolate. The base deprotonates that CH and forms a stabilized carbanion. Because of resonance, most of the time, that negative charge will probably be on the oxygen of a carbonyl. But let's just represent it as a carbanion here. In the aldol reaction, that carbanion can be shown to react with an aldehyde. When it does, the electrons leave the carbon, they push through the CO double bond onto the oxygen of the aldehyde, more electronegative atom, lower potential than the carbanion that we started with. We form a nice stable CC bond. That is the aldol process. It's as simple here as I can possibly make it for base catalyzed aldol reactions. That representation is probably not going to satisfy your organic chemistry prof. That prof almost invariably will want you to master the art of drawing enolates. But enolates can look different according to what the electron withdrawing group is. So let's go through a few examples. In enolate chemistry, as in a lot of chemistry, it's very good to align the arrows trans-antiperiplanar, so you can feel a wave of electrons flowing from high potential to low potential, from a base to an alkoxide. But actually that could be made much more complicated because deprotonation feeds in electrons to the pi star of the carbonyl. Too advanced. Don't worry about that, but it's coming if you stay with chemistry. So then aldehyde enolates are simply represented like this. That's the analog of the enol chemistry that I showed in my previous video. To modify this diagram then for esters is very simple. We just put an OR group on the carbonyl, but the reaction flow of electrons is almost identical. Base deprotonate C alpha, form a CC bond, put the electrons on the oxygen of the carbonyl, changes the carbon next to the electron withdrawing group into a nucleophile. This is so easy then. If I want to make an enolate of an amide, again, line up the electron flow trans-antiperiplanar, show the base coming in to deprotonate next to the electron withdrawing group, next to the carbonyl, form a CC bond, and put the electrons onto the oxygen of the alkoxide. Note here that I've chosen a dialkyl amide, so I'm avoiding the complication of deprotonation of NH, which can happen for other amides. Enolates can be formed from nitriles. So if we take a nitrile, again with an acidic CH, next to the CN triple bond, the base can come in trans-antiperiplanar, shifts electrons around from that CH bond as it deprotonates to the CC bond, takes the triple bond down to a double bond, and puts the negative charge this time on a nitrogen. It looks different, but it is an enolate formation, even though there's no carbonyl involved. Okay, now we're all zen with the art of forming enolates. We know what's going on. And of course, in aldol chemistry, the electrophile is going to be an aldehyde or a ketone. The flow of arrows proceeds from the alkoxide. Put your pen where the electron density is. That's what I always tell my students. And push, 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 reform a nice CO double bond, high in energy. Break the CC bond, that costs you, but push the electrons around towards the aldehyde carbon. The aldehyde is acting like an electrophile, and on to the oxygen of the aldehyde gives us an alkoxide via the Aldol process. Of course, this reaction is more complicated if that aldehyde can enolize. We don't want that. We don't like complications in organic reactions. So choose an aldehyde which can't enolize, or use a biochemical reaction where you can force one enolate to happen as the aldehyde reacts. Again, simple repetition. We don't have to use an enolate from an ester. I've switched it here to an enolate from a thioester. I like that one because remember, enolates from acetyl-CoA are very important in metabolism. Push, 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 the electrons from the O- form a CO double bond, break the CC bond, push the electrons through to the carbonyl carbon and on to the oxygen of the aldehyde. Aldol process, just the same. It's just one substituent is different. And if I change that substituent again to amide enolate that we generated before, push, push, push in the same way, reform a CO double bond, same thing, break the CC bond, same thing, form a CC bond from the C alpha carbon to the carbonyl, and thus generate an alkoxide. People worry about, is the product then an alkoxide or an alcohol? Don't worry about that. Chemists will put the product in a separating funnel and they'll shake it up under slightly acidic conditions. Protons will be available and the alkoxide will simply protonate to the alcohol. So in an exam, you could show the alkoxide and then protonation in a separate step. Nitrile enolates look different, react the same. This time, we're putting our pen on the electron density, which is the nitrogen. Push in and regenerate that triple bond, break the CC bond just the same way, and form a CC bond to the aldehyde, break the CO of the aldehyde, alkoxide. We have our aldol product. I've drawn the curly arrows for these slides using ChemDraw, and it takes a little bit of practice to draw those curly arrows. I've produced a video telling you how, right here. But the main point for you is think like an electron. Electrons move in wave, and the straighter the wave is, the lower the energy of the flow of electrons. You don't have to, at introductory organic level stage, show the electrons beautifully aligned, but think that way, because they are when they flow in organic chemistry reactions. So using ChemDraw then, I've tried to represent a wave flow for that nitrile aldol reaction using arrows like this. Can you feel it? Flowing from the nitrogen on to the more electronegative, lower potential oxygen. Okay, close that folder on your hard drive. Forget enolate chemistry, now we're going to drop the pH. Acidic conditions, we're talking about enol chemistry. Enol formation I already described for acetaldehyde in my first video. It's not a big intellectual jump to use the same set of arrows for, say, acetone. First of all, protonate the carbonyl to activate. Always think that way under acidic conditions at low pH. That protonation facilitates spontaneous loss of the CH next to the carbonyl. You can show it by using water as a base, but you're not allowed to show it using hydroxide as a base. Hydroxide doesn't exist under acidic aqueous conditions. All hydroxide would be protonated, but you can use the lone pair of an oxygen if you want to. A minimalist way to show it, which may be satisfactory for your prof, is just to show spontaneous loss. Push the electrons in, form a CC bond, push the electrons out to satisfy the oxonium positive charge, make it into a neutral OH of an enol. I don't want to bore you too much, but let's just put different substituents on. In acetone, we have two methyl groups. In a thioester, we can have an SR group. And remember, thioesters are related to acetyl-CoA. Keep thinking about that. Again, same process. Protonate on the carbonyl of the thioester facilitates loss of the C-alpha H, CC bond formation, break the C double bond O, satisfy the positive charge, and gives an enol, which looks different because it's the enol of a thioester. So let's consider a nitrile, just because it looks different. Protonation at this time on the nitrile nitrogen. Protonate to activate. That activates loss of the C-alpha, form a CC bond, push the electrons of the triple bond onto the nitrogen, satisfy the positive charge of that. That gives us a ketenamine, which is, if it has an NH substituent, an enol form. To show the reaction of the enol, we take the electrons away from the NH bond, liberate a proton, push them in to reform the cyanide triple bond, break the CC bond next to that. The electrons throw through the carbon, the C-alpha, and react with the aldehyde. We formed a CC bond, that's great. The aldehyde, CO electrons move up to the oxygen, which is protonated, and satisfy the charge there. Please don't show hydroxide or other strong bases under acidic conditions in enol chemistry. That will lose you points in the exam. In the reaction of these enol forms, all of them, we're going to react under acidic conditions with an aldehyde. The aldehyde should be shown protonated because the protonated form is by far the most reactive, and that's what's driving this reaction. So in all those cases, we show protonated oxonium form of the aldehyde reacting by taking electrons away from the proton attached to the oxygen, reforming a CO double bond, and breaking the CC bond onto the aldehyde, protonated, break the CO bond there, and neutralize the charge. Things look a little bit different for nitriles. We're just taking an NH and using the electrons to flow through there, but it's conceptually almost identical. I hope now you'll never be fazed by forming enols in an exam question and reacting them with an electrophile. You may think you've got it. In practice, you may not. And please, take a look at my workbook where I show lots of examples of reactions of enols and enolates with aldehydes in Aldol chemistry. Thank you very much for listening. Good luck with your studies. Bye-bye.
The days I could speak my mind. Now I'm a ghost, lost in the grind. Shackled by silence, can't break free. Echoes of my voice, just memories. Stomping on my pride. When I miss the days I could speak my mind. Now I'm a ghost, lost in the grind. Shackled by silence, can't break free. Echoes of my voice, just memory.